Hello, how are you? Uh, some more discussion about the transformation of stress and strain. Uh, Here in these slides, we will be discussing the transformation of stress and strain for a 2D problem or plane stress problem. So, meaning that the loading is only in one plane or along two axes. In the third axis, there is no loading. So such problems are actually classified, or these are known as plane stress problem. Here on the slide, you could see a stress element. Stress element is actually the diagram which represents the state of stress within the material or state of stress at a point inside the material. So this stress element here, which is represented by a square, it actually represents the condition or state of stress within the material. It represents a point or a particle inside the material. So some stress values are given. Actually, the coordinate frame is not given. So first of all, in such cases when the coordinate frame is not given, so it is better you draw the coordinate frame. So I am drawing the Cartesian coordinate frame. So let's say this is x-axis, this is y-axis, and the z-axis is actually perpendicular to the whiteboard. So this is actually a Cartesian coordinate system. So let's read the statement of the problem. For the state of plane stress shown, that is shown in the figure, determine the principal planes. So we have to determine the principal planes, meaning that the principal axes, sigma maximum, sigma minimum, or sigma 1 or sigma 2 in this case. The principal stresses, meaning that we have to find the quantitative values or magnitude of the principal stresses which are acting along the principal planes or principal axes. Part C, the maximum shearing stress. So we have to find out the value of the maximum shearing stress and the corresponding normal stress. And the corresponding normal stress, as you know, that it is average. The corresponding normal stress along the maximum shear stress is average stress. So you have to find out the average stress. So in order to do such problems, so we have a number of methods. One of the methods that we have discussed is the analytical method, in which we use the algebraic equations to find out or determine the state of the stress in any coordinate frame, or with which you could find out the principal stresses, principal planes, etc. So the stress element is given. So basically, as I told you, that normally the axes are not given, so you could take the axes. We have to find out the orientation of the principal stresses. So this is the analytical model which could be used to determine the orientation of the principal axes. So here you could see that tangent to theta p is equal to 2 times tau xy divided by sigma x minus sigma y. Sigma x is the normal stress along x-axis. Sigma y is the normal stress along the y-axis. And tau xy is the shear stress which is actually acting on the stress element. The subscript p represents the principal axis. So meaning that we have to find out theta p from this equation, which would give you the orientation of one of the principal axes. And this analytical model is used to determine the stresses along the principal axis or axis. So it would return, this analytical model would return two values, one with the plus sign and the other with the minus sign. With the plus sign, it would return the sigma maximum, and with the minus sign, it would return the sigma minimum. Next, part C, which you have to find out. This is the analytical model for the maximum shear. So it is sigma x minus sigma y by 2 whole square plus tau xy square whole under the root. So this analytical model you could use, and the corresponding normal stresses associated with the maximum shear stress is the average stress. So for that you could use this analytical model. Now, as the coordinate axes are not given, so we are choosing this coordinate axis. This is x-axis, this is y, and the z-axis is perpendicular. But since the problem is biaxial problem or two-dimensional problem or plane stress problem, so for that it is not necessary to mention the z direction. So depending upon this coordinate frame, this would be sigma xx or sigma x. So sigma xx or sigma x is actually plus because it is tensile. As you could see, it is tensile loading or tensile stress. So plus 50 MPa, megapascal. And along y-axis, you could see this normal stress. And as you could see very easily, that it is a compressive stress, and its magnitude is 10. So you have to put minus sign for the compressive stress. So sigma y is equal to minus 10 megapascal. Now coming to the shear stress, if you look at this shear stress, so normally, as you know that we use two subscript. The first subscript represents the unit vector normal to the surface or normal to the area. So that is that surface, if you consider this surface or this area, its unit vector is actually in x-axis. So the first subscript is x, whereas the second subscript represents the direction of force, which is actually the direction of stress. So the direction of stress or direction of the force is actually in this direction, that is in positive y direction. So the subscript that we would be using here with the shear stress is tau xy is equal to. Now, if you look here, this shear stress is counterclockwise. Tau xy is counterclockwise. So actually, which sign we have to put with this shear stress, plus or minus? Since we are working in the Cartesian coordinate system, and also in order to find out the direction of this couple, this is a couple. Look here, this is a force or stress, this is a force or stress, it is a couple. So if you encircle, if you take your right hand or encircle your fingers in the direction of the couple, in the direction of the forces, in the direction of the stress, then your thumb will direct in the direction of the couple. It would represent, it would be in the positive z direction. It would be in the positive z direction. So since it is in the positive z direction, when you encircle your fingers and point your thumb, it would represent a positive z direction in the Cartesian coordinate system. So we need to put a positive sign here. Second reason, since when we are doing the derivation or when we are actually devising the analytical models, so in that we took the counterclockwise shear stress as positive. So here, remember that when you are doing these problems analytically, so you have to take the counterclock shear as positive, whereas the clockwise shear stress as negative. So here tau xy you have to take it positive, whereas the tau yx, which is actually equal in magnitude to tau xy, however, it would be opposite in direction to tau xy, meaning that tau yx would be opposite to tau xy in direction. And the reason we have already discussed in previous lectures, because actually when the material is loaded, the particle in the material is not rotated. It is not rotating. It is completely stagnant. It is completely in equilibrium. It is completely in statics. So which means that the counterclockwise moment must be equal to clockwise motion. So using that analogy, we could easily say that the cross shears, these are known as the cross shears, they would be always equal in magnitude but opposite in direction. So once the notations are allocated to the stress values, then it is very easy. The rest of the problem is very easy. So using the analytical model for the orientation of the principal axis tangent to theta p is equal to, you need to just plug the values. Tau xy is plus 40, sigma x is plus 50, and sigma y is minus 10. So after plugging the values and after doing the calculation, the answer is 1.333. And then you have to take the tangent inverse on both sides of the equation. So 2 theta p would comes out to be 53.1 degree. And then if when we divide this by 2, so theta p is equal to 26.6 degree. So it means that this is one of the principal axis. This is the angle which one of the principal axis is making with this x-axis. One of the principal axis is making an angle of 26.6 degrees with the x-axis. So this is one. This is the orientation of the one of the axis, one of the plane. Actually, how to find out this equation would return one value, but we know that the principal axes are also perpendicular to each other. The angle between the principal axes is 90 degrees. So if the this is the first principal axis, so the second principal axis would be at an angle of 90 degree to the first principal axis. So you just add 90 to 26.6 degree. So we would get the second principal axis, which would be 116.6 degree, 106 degree. So this is the angle which our second principal axis is making with the x-axis. So the first principal axis is making an angle of 26 degree. However, the second principal axis is making an angle of 106 degree. It would be more clear in the coming slides. Next, we have to plug the values in this analytical model in order to find out the values of the principal stresses. So just plugging the values, and then after doing the calculation with the plus sign, we would get sigma maximum. Sigma maximum is equal to plus 70 MPa, meaning that tensile. And sigma minimum, when we would use this minus sign and then do the computation, then sigma minimum is equal to minus mean it is compressive. Our second principal stress, sigma minimum, is actually compressive, and it is minus 30 MPa. Next, we have to draw the stress element showing the principal stresses, showing the principal axis. So in order to draw, here it is already drawn. So I would just tell you the procedure that how we would draw this principal, the stress state for the principal stresses. So first of all, what you have to do? You have to draw a horizontal line representing x-axis. So here you could see a horizontal line, it is representing x-axis. Then next you have to draw a line at an angle of 26.6 degree theta p. It is the orientation of one of the principal axis, which we have already calculated in the previous slide, 26.6 degree, and it is plus. So normally we take the angle along the with respect to x-axis, and positive angle is counterclockwise. Positive angle is always counterclockwise, and the reason is again same. If you encircle your finger counterclockwise, then actually your thumb would be in the positive z direction. It would be in the positive z direction. So it is positive, so it would be counterclockwise. So we have to draw a line at an angle. So just draw a line at an angle of 26.6 degree to x-axis. Let's say this is our x-axis, which you have drawn, and then at an angle of 26.6 degree, I have drawn a line. Next, we have to draw this square. So perpendicular to this line, draw a line. So this is the line which I have drawn perpendicular to that. And next, to this line perpendicular, draw a perpendicular line, this line, and then again to this line as a base or as a datum, draw a perpendicular line, this one, and then draw this line in order to complete the square. So then you have to draw the square, and next you have to complete this. So this is actually the tensile stress sigma maximum. This line or this arrow represents the tensile normal principal stress sigma maximum plus 70 MPa. So you have to put the arrow in this direction. Similarly, another arrow in this direction in order to show the tensile normal stress. The first principal stress 70 megapascal, and then we know that the second principal stress is 30 MPa, but it is compressive. So put the arrows in the here in the downward direction. So putting that arrow and then that arrow, so that it is clear that it is compressive stress. So this is sigma maximum, this is sigma minimum. One principal stress, the second principal stress. The orientation of this is the one of the principal axis, and this is the second principal axis. The second principal axis is perpendicular to the first principal axis. So there is an angle of 90 degree between these two axes, or between these two axes. So that is 90 degree. This angle, which we have already calculated, 26.6 degree, and the angle which our second principal axis is making, that angle is this one. That angle is this one. So this angle is 90. So if we add this 90 to 26.6 degree, so what we would get? We would get 116.6 degree, which we have done on the previous slide. So here you could clearly see both of the principal axes. The first principal axis, where sigma maximum is 70 MPa, its orientation is 26.6 degree. However, the second principal axis has an angle of 116 with this x-axis, and the angle between the principal axis, you could clearly see it as 90 degree. Next, we have to find out the maximum shear stress. So this is the analytical model. Just plug the values and then do the calculation. So the maximum shear stress comes out to be 50 MPa. And the orientation of the maximum principal stress with respect to x-axis. This is the analytical model. Tangent to theta s is equal to sigma x minus sigma y divided by 2xy, and there is negative sign here also. After plugging the values and then after doing the calculation, you would get, and then taking the tangent inverse, dividing by 2 on both sides, theta s would comes out to be minus 18.4 degree. But remember that again, normally there would be two there will be two axes along which the shear stress would be maximum, and those two axes are also perpendicular to each other. The angle between those two axes is 90 degree. We would see here when we would be drawing that stress element. So the angle or orientation of the second plane or axis where the shear stress is maximum, it would be at an angle of 90 degree to the first axis where the shear stress is maximum. So to this angle, you just add 90 degree. Here just at 90 degree. So our second angle would be 71.6 degree. So these are the orientation of the axes where the shear stress is maximum. The corresponding normal stress associated with the maximum shear stress is average. So sigma prime is equal to sigma average, sigma x plus sigma y divided by 2. Just plug the values, and sigma average or sigma prime or the normal stress associated with this maximum shear stress is 20 MPa. Next, again, we have to draw the stress element representing the maximum shear stress and the corresponding normal stress. So first of all, just draw a horizontal line representing x-axis. Now look here, theta s is minus. So minus is normally with respect to x-axis. Minus, since plus we are taking counterclockwise, so minus angle we have to take clockwise. So with respect to x-axis, take a clockwise angle. So measure the angle in the clockwise direction, in this direction. Here it is written theta p, but it is actually theta s. So theta s is equal to minus 18.4 degree. So just draw this line. Just draw this line. And to this line, draw a line which is perpendicular to this line. So that is actually just draw it perpendicular. And then complete this square, which would represent the stress element. So complete this square. And after completing this square, since sigma prime is plus, so it is tensile. So put the arrow in this direction and put another arrow on the opposite face of the square, and it is representing the normal stress and which is tensile. So again put the arrow in this direction. Next we have to put the shear stresses. Shear stresses. So tau maximum along this face, put this arrow which is representing the shear stress, and on the opposite face put the direction of the arrow in the opposite direction. If this shear stress is counterclockwise, the other shear stresses on the other faces would be clockwise. So draw those shear stresses. So this is a shear stress, maximum shear stress, sigma maximum 50 MPa, and also this is a shear stress, maximum shear stress 50 MPa. On this axis or on this face, you have to also draw the normal stresses. Normal stresses tensile 20 MPa. So it should be the arrow should be outward. So just draw those and write that sigma prime is equal to 20 MPa. So this would actually complete the stress element. This is the stress element. This would complete our stress element, and this stress element represents the axis where the shear stress is maximum and the normal stress or the corresponding stress is the average. And you could again see this is one of the axes along which the shear stress is maximum, and this is the other axis along which the shear stress is maximum, and the angle between these two axes is actually 90 degree. It is 90 degree. So this angle, look here, this angle is how much? This angle is minus 18.4 degree. And if you measure this angle this line is making with, or this axis is making with the x-axis, it would be 71.6 degree. It would be 71.6 degree.